Hi, I'm Professor Kelly, and this is a lecture on context-free grammar for CSCI 308 Programming Language Design, and the first lecture in the Syntax and Semantics module. Learning goals for this lecture are to be able to describe the theory behind context-free grammar, distinguish context-free from regular or context-sensitive grammars, and apply context-free grammar to generate sequences. Semantics and syntax, or meaning and grammar. The difference between the two can be illustrated by these two quotes from two equally wise old men, Yoda and Noam Chomsky. Yoda, an alien from the Star Wars franchise, is known for his distinctive manner of speech. For example, "Named must be your fear, before banish it you can." While the meaning is clear, the way Yoda has phrased it violates the rules of English grammar. Properly in English, it should be, "Your fear must be named before it can be banished." Noam Chomsky came up with the sentence, "Colorless green ideas sleep furiously," to help illustrate the difference between semantics and syntax. "Colorless green ideas sleep furiously" is syntactically correct in that it follows all of the rules of English grammar, but it doesn't have any clear meaning because of the contradiction in the words. What does it mean to sleep furiously? What does it mean for an idea to have the color green? What does it mean to have something that is both green and colorless? In programming languages, semantics is the meaning of the program, what is being executed by the computer, how it can be represented mathematically, whereas syntax is the form the language takes. Python, Haskell, and so on have different forms, but potentially have the same meaning depending on the code. A grammar is a set of rules for putting symbols together to form a sequence. For example, brackets 1 plus 2 times 6 minus 3 follows the rules for math, whereas 1 plus bracket plus times 5 bracket does not follow the rules for math grammar. The monkey ate a banana follows the rules for English grammar. Conversely, banana monkey ate the does not. Grammars can be classified by their complexity. Noam Chomsky proposed a hierarchy defining grammars from most simple to most complex. The most simple grammar is the regular grammar. Regular grammars have the expressive power to describe simple games such as tic-tac-toe, connect four, and rock, paper, scissors. At the next level, we have context-free grammars. Context-free grammars have enough expressive power to describe all programming languages, such as Haskell, Python, and so on. Each level of the Chomsky hierarchy includes all grammars at the lower level. Anything that can handle context-free grammars can also handle regular grammars. At the next level is context-sensitive grammars. Context-sensitive grammars includes all natural languages, English, French, Mandarin, and so on. At the highest level of the Chomsky hierarchy, we have unrestricted grammars, which describe anything that is computable. To represent grammars, we're going to use Backus-Naur form, a standard notation used in computer science. In Backus-Naur form, a rule is represented as a symbol on the left-hand side, followed by an arrow indicating the symbol can be replaced with what follows on the right-hand side. A vertical bar is used to represent options, such that a symbol can be replaced by this or by this. Terminal symbols, represented using uppercase letters, are symbols that cannot be replaced by any of the rules. Non-terminal symbols, represented using lowercase letters, are symbols that can be replaced by one of the rules. The start symbol is a special non-terminal symbol that is used to start the grammar. Common names for the start symbol are program, if it's a program, or sentence if you're creating a sentence. Let's play rock, paper, scissors. Rock, paper, scissors can be represented using these two rules in Backus-Naur form. We start the game off with the start symbol. Because this is a game, let's call the start symbol game. We can replace the start symbol with either rock round, paper round, or scissors round. Let's play rock first. We replace game with rock round. Now, rock is a terminal symbol, which means we cannot replace rock. We are committed. We have played rock in the first round of the game. However, round is simply a non-terminal symbol indicating that we can play another round if we so choose. To play another round, we apply one of the parts of the round rule, replacing round with either rock round, paper round, scissors round, or nothing. Nothing would indicate stopping the game. Let's continue for now. Let's play paper. We replace round with paper round. We can play another round again by replacing round with something else. Let's say rock round this time. All right, we've played 3 rounds of rock, paper, scissors. We've played rock on the first round, paper on the second round, and rock on the third round. I think that's enough rock, paper, scissors. So let's use the last part of the round rule and delete the round symbol. And now we've created a legal sequence of rock, paper, scissors plays. Regular grammars, such as the grammar that describes rock, paper, scissors, only allow rules of the following 3 forms. A rule where a non-terminal symbol is replaced with a terminal and non-terminal symbol. A rule where a non-terminal symbol is replaced with a terminal symbol, or a rule where a non-terminal symbol is replaced with nothing. A context-free grammar is more expressive. It allows all rules of the form non-terminal symbol is replaced with whatever we want to replace it with. For example, consider this one-rule grammar that allows us to create pairs of round brackets or curly brackets. How do we use this grammar to make a pair of nested round brackets followed by curly brackets? We start with the start symbol, exp, short for expression. The first thing we want to do is we need to create 2 expressions. 2 expressions allows us to have 2 independent sets of brackets, the round brackets and the curly brackets. We can replace the first expression with expression surrounded by round brackets, and then we can do that again, and then delete the first expression. The second expression we can replace with expression bracketed by curly brackets, and then delete that expression as well, and we have the end result. Context-free grammars can capture much of the syntax of natural languages. Here's a simple example. Let's start with the start symbol, sentence. We can replace that with noun phrase and verb phrase. The noun phrase can be replaced with determiner and noun. Determiner can be replaced with the or a in this simple grammar. Let's choose the. Noun can be replaced with banana or monkey. Let's choose monkey. The verb phrase can be replaced with either a verb or a verb and a noun phrase, the second noun phrase acting as the object of the sentence. Let's do verb and noun phrase. The verb can be replaced by ate, and the noun phrase can be replaced by determiner and noun. Here we have choices again. Let's go with a for the determiner and banana for the noun. We end up with the sentence, the monkey ate a banana. This isn't the only sentence possible with this simple grammar. If we made different choices, we could end up with a banana ate a monkey, or if we didn't want the noun phrase object, we could just have a banana ate. However, to capture all of the complexity of English or any natural language, we would actually need a context-sensitive grammar. Context-sensitive grammars allow for rules that only apply in a certain context. In a context-sensitive grammar, all rules are the form left context, non-terminal symbol, right context, maps to left context, something, right context. In other words, we can replace the non-terminal symbol with something contingent on the left and right context. This rather complicated looking tree for the sentence, the dog bit John, illustrates using a context-sensitive grammar to parse English. Note that the is no longer simply a determiner. The's type is MP/N, meaning the can be a noun phrase if it is combined with a noun. Unrestricted grammars are the most powerful. They describe anything that is computable, that is, anything that can be implemented by a Turing machine. All rules are the form something to whatever, where something is any non-empty sequence of symbols, and whatever is any sequence of symbols, including an empty sequence. Context-free grammars have many applications. The one most relevant to this particular course is, of course, designing programming languages, interpreters, or compilers. However, context-free grammars are also useful for understanding human languages, for sequencing the RNA of viruses such as COVID-19, and for explanatory AI as a tool for explaining how very difficult to understand artificial intelligence systems such as deep learning actually work. Context-free grammars can also be used to create computer art. For example, this grammar here defines this art object. The Chomsky hierarchy classifies formal languages by their complexity. A regular grammar consists of the rules non-terminal to non-terminal and terminal, non-terminal to terminal, or non-terminal to nothing. A context-free grammar is much more loose. It allows you to map a non-terminal symbol to whatever you like. Context-sensitive grammars allows you to check what's to the left and to the right of the non-terminal symbol before applying the rule. An unrestricted grammar is more powerful still.